right. I'm Caleb, and I'm a PhD student at the University of New Mexico, and I'm doing my research at Sandia National Labs with Peter Schwint, and I'll be talking about a dead zone free gradiometer in the Earth's field. So, why are we trying to do this? Why are we trying to make a gradiometer in the first place? Why are we trying to, make a gradiometer, right? So we want to make a direct optical measurement of a magnetic field gradient from a single optical signal. We want to have high load rejection, so we want to reject the Earth's field, and we want to retain high sensitivity after we reject. And applications of this include magnetoencephalography and magnetocardiography, right, measuring magnetic fields in the brain and the heart. And we're going to do it without a shield, right? We want to do it in an ambient environment. So the basic idea behind this gradiometer setup, we have two vapor cells separated by some distance d. We prepare the atoms in such a way that when a weak carrier beam comes through the first cell, it generates a sideband. And this sideband is offset from the carrier by the hyperfine frequency plus a term related to the magnetic field. And as it goes to the second cell, another sideband is generated. And that second sideband is also offset from the carrier. But there's also a splitting between the first sideband and the second sideband. And then, since the sidebands are orthogonally polarized to the carrier, we can filter out the carrier light and let the sideband pass. So we have two sidebands, the carrier light's filtered out. We produce a beat note where the frequency of the beat note is proportional to the magnetic gradient. And kind of the main ideas behind this sideband generation came from a paper from Henry Tang in 1973. And the idea behind this gradiometer, or the patent behind this gradiometer system, came from Vishal Shah pretty recently in 2018. So a more detailed description. So we're going to come in on the D1 line with a 795 pump, and on the D2 line with a 780 carrier. The pump is going to be orthogonal in direction to the carrier, and it's going to be circularly polarized. So we're going to try to optically pump the atoms using that circularly polarized pump. We also have an 87 rubidium cell with 30 torr of nitrogen and a 87 rubidium cell with 15 torr of nitrogen. And I'll talk about why we have different buffer gas pressures in a little bit. We also use a polarization selector so that we can pass the sidebands through. And I want to talk about the gradiometer process a little bit to let you know how this system works. So the atoms actually start on the ground, in the ground states. There's no pumping, right? So the populations are spread out along the MF sublevels. And then you have a sigma plus polarized pump that comes through that pumps the atoms to the end state, because when they go to the excited state, they gain an MF level, an MF level as they go up to the excited state, they fall back down. So the population ends up getting biased toward this side of the manifold. And this is a dark state because sigma plus light cannot take the population out of the state. And then we apply a pi over 2 pulse of magnetic energy. This generates a coherent superposition of our atoms. And then we send in a weak carrier. And if this carrier is at, say, the F equals 1 ground state, it comes up to the excited state, and a sideband is generated. This sideband is orthogonally polarized to the carrier. And it's also separated by 6.8 gigahertz, which is the hyperfine frequency, plus also the splitting from the Zeeman sublevels. And then we beat these two sidebands together, right? Because there's two sidebands generated, one in this cell, one in this cell. So here's our sideband, our gradiometer signal. This is a single optical signal from two separate vapor cells. The frequency of this beat note is 7 kilohertz plus this term that comes from the Zeeman splitting. This 7 kilohertz term actually comes from the buffer gas shift, from the fact that this 87 rubidium cell has 30 torr of nitrogen, and this one has 15 torr. So you get a frequency shift on the hyperfine. And we do this because at zero field, right, you want to be able to still get a beat note that you can measure the frequency out of. So if it was, say, 0, it'd be hard to measure a frequency that's very small. And our collaborators at QSpin have actually developed a physics package based on this model I've been talking about. The pump comes in here to the side. We have 2 vapor cells, one at 30 torr, one at 15, and the carrier comes straight through. And from this system, we've been able to get a field gradient noise reading of 20 femtotesla per root hertz, and that's divided by the 4.4 centimeter separation between the 2 cells, which is pretty good for a hyperfine magnetometer or gradiometer. So, talk about these results, but how do we know we're actually seeing a sideband from a coherence? So at 0 to tuning, we're right on resonance with our microwave field. These are some oscilloscope pictures of the microwave frequency being turned on. The yellow curve is the sideband, and the gray is the MODR signal, where an MODR signal tells us the amount of population in a sublevel. So at 0 to tuning, the sideband actually oscillates at twice the frequency of the MODR signal. And our reasoning behind this is, as you go through a Rabi oscillation, the sideband amplitude is maximized twice, because in a coherent superposition, the sideband is maximized. So when you do a pi over 2 pulse, you're in the 2-2, you come down to this equator, and as the Rabi frequency is coming around, the sideband is maximized twice during a single Rabi frequency evolution. If you detune from the equator, you get kind of a funky looking sideband feature, because, well, you're not equally going through the equator anymore, or right, you're going through at some random spot. You may not know exactly where you're at, so the frequency is kind of jumbled. And then if you're far detuned, you may actually, like your block vector or spin vector may actually not even be getting down to that equator at all. So your sideband is actually oscillating at the frequency of the MODR signal, because when it comes down through it twice, you get it maximized twice during a Rabi frequency, and when it's coming through not at all, or maybe once, then it's at the same frequency. So now that we have this working system, can we make it more compact? Answer is maybe yes, but it's a little more difficult. We need to add a dual wave plate, and we're going to have the pump and probe along the same axis. So we're not going to come in with an orthogonal pump anymore. So this dual wave plate is actually circularly polarized at 795. It's linearly at 780. So we're still pumping to the end state in this case. And then we have a filter that lets the 780 nanometer laser pass, which is the carrier light, which contains the sideband. And then we have a polarizing beam splitter, which actually blocks the carrier beam and lets the sidebands through. All right, so why is this difficult? So the first case, if our ambient field, say, is perpendicular to the direction of our laser beams, we can't really optically pump to the end state anymore, right? Because if your quantization axis is that way, your atoms aren't really seeing circular polarization in the same way they were before, so you don't get good optical pumping to the end state. And in case 2, if your magnetic field is along the axis of the beams, then you actually can't generate a sideband on the transition we were talking about earlier. You have to come to this delta MF equals 0 microwave transition. Because when you come up to the excited state, your sideband falls down. It can only be a sigma plus or minus transition. So you can only use this state. So somehow we need to get our population down to this level, right? Like here, we're optically pumping to the end state. So how do we get our population down to here? I'm going to talk about these two cases and how we're going to solve that. So if the ambient field is perpendicular to the laser axis, right, we turn on a magnetic field BC, and we adiabatically ramp down BC so that the quantization axis actually rotates towards the ambient field. So it starts out along the direction of the laser and then rotates towards the actual ambient field we want to measure. And here's the total magnetic field. You can think of this as just a reference frame shift on your block sphere. We want to do this slow enough so that the spin vector adiabatically follows the torque vector, right? And then we do our pi over 2 pulse just like before, generate a sideband, and all the selection rules work, and it works perfectly. The results of this, here we're actually going to look at the MODR signal, which I explained before, is going to tell us the amount of population in some of our states. This is the 2-to-1 transition. We're sweeping the microwave frequency. So we know that most of our population is sitting in that end state here. We're still optically pumping to the end state, but we still have some population in these other states. We're about 90% of our population's in the end state. And here is our sideband produced. This is a single cell experiment. In comparison, I want to describe another experiment where, let's say you just do hyperfine pumping, and you bring all the population to this F=1 level, and you're not actually getting all the population down to this state, or into this state, then you can see the sideband signal is much lower. So we see a 10 times improvement if we do this method, this quantization axis rotation method. And case 2 is when the magnetic field, the ambient field we're trying to measure, is along the axis of the laser. In this case, we're actually going to use adiabatic rapid passage. So we're going to transfer the population from the end state to the state down here by sweeping through a resonance. And you can either sweep through the resonance by changing the microwave frequency, or you can actually change the level itself up and down, right? So we actually choose to sweep the magnetic field, which is changing the spacing between the levels. So as we sweep through, we have 2 microwave pulses. These pulses are at the same frequency. They're tuned to this F=1 level, F=2 1 transition. So as the magnetic field sweeps through, our population is actually transferred to this state, and then we apply another pi over 2 pulse, generate our sideband. Just like before, we have a pump. This is data. We have the arc pulse, which transfers the population. We have some induction in our coils, so we see these little abnormalities. And then we have a pi over 2 pulse to generate the sideband. And here's the results. So you can see, just like before, I'm comparing it to the ARP experiment, or the ARP experiment to the hyperfine pumping experiment, right? So in this case, there's about a 4 times improvement using this ARP method. So, a comparison to these 4 experiments. This is the quantization axis rotation. This is the ARP, and these are the 2 hyperfine experiments. You can see that our methods that we've used significantly has enhanced the sideband signal, which in the future we can use to enhance our beat note signal. But we're not quite sure why the ARP is not at the same amplitude as the quantization axis rotation experiment. And we think that's because we have an inefficient ARP process. So we measure a magnetic gradient from a single optical signal. We demonstrate 20 femtotesla per root hertz times centimeters in the Earth's field with no shield. And we're going to work towards dead zone free operation of this gradiometer. And we're going to show how we can make that setup more compact while still maintaining dead zone free operation. And in the future, we actually may want to computerize this. And we want to understand that discrepancy between our ARP sideband and our quantization axis rotation sideband that we produced. So, acknowledgements. At Sandia, Me and Peter Schwint are working. The PI on this project is a Vishal Shah Q-spin and Yingzhu Wang, and some theory help from Igor Savikov. Funding from this is from DARPA, so I'd like to thank the ambient program. And postdocs are available if you are interested. Talk to Peter Schwint. Thank you.